In a frozen valley 15 kilometers outside Kanggye, North Korea, on June 28, 1952, a rifle exploded in Sergeant Kim Il-sung's hands with such violence that fragments of metal tore through his right arm and chest, ending his military career and nearly his life. The weapon that detonated wasn't an American M1 Garand. It was North Korea's desperate attempt to copy one. A crude imitation built from inferior steel and manufactured with equipment that couldn't hold the necessary tolerances. What should have been a straightforward reverse engineering project had become a cascade of failures culminating in catastrophic violence, teaching North Korean engineers a brutal lesson. Some technologies cannot simply be stolen and reproduced without the industrial infrastructure that created them. This is the story of ambition colliding with reality, of revolutionary fervor meeting the unforgiving laws of metallurgy and physics.
The rifle that defined modern warfare. The M1 Garand rifle represented a quantum leap in infantry firepower when it was adopted by the United States Army in 1936. Designed by Canadian-American engineer John Kanggye Garand, after years of painstaking development, it was the first semi-automatic rifle to be widely issued to infantry forces, replacing the bolt-action Springfield M1903 that had served American troops through World War I and beyond. The rifle's specifications were impressive for its era. It weighed 9.5 pounds unloaded, measured 43.5 inches in length, and fired the powerful .30-06 Springfield cartridge from an 8-round N-block clip at a cyclic rate limited only by how fast the shooter could pull the trigger. Unlike bolt-action rifles that required manual cycling between each shot, the Garand automatically ejected spent cartridges, chambered fresh rounds, and was ready to fire again in a fraction of a second. This gave American soldiers an overwhelming advantage in sustained firefights. While enemy soldiers armed with bolt-action rifles were working their actions between shots, American troops could maintain continuous aimed fire. By 1952, when the Korean War had settled into a bloody stalemate along the 38th parallel, the M1 Garand had proven itself in combat across two major conflicts. It had stormed the beaches of Normandy, fought through the Pacific Islands, and was now the standard weapon of American and many Allied forces in Korea. Chinese and North Korean troops, armed primarily with Soviet bolt-action Mosin Nagant rifles and some PPSH submachine guns, found themselves consistently outgunned in medium-range engagements, where the Garand's combination of accuracy, power, and rate of fire proved decisive. North Korean military planners recognized this disparity with growing alarm. Combat reports from Chinese volunteer forces fighting in Korea consistently mentioned the devastating effectiveness of American rifle fire. Captured American weapons were studied intensively, and requests went up through military channels for domestic production of equivalent weapons. The Soviet Union had provided substantial military aid, but Soviet weapons doctrine still emphasized the bolt-action rifle, supplemented by submachine guns. The SVT-40 semi-automatic rifle had seen limited service, but had been largely withdrawn due to reliability issues in field conditions. The opportunity to acquire intact M1 Garands came in late 1952, when Chinese forces overran an American supply depot during a nighttime raid. Among the captured material were 17 M1 Garand rifles in various conditions, along with several cases of .30-06 ammunition and some technical documentation. The Chinese, who had their own weapons production priorities and generally preferred simpler designs suitable for their industrial capabilities, were willing to provide 3 of these captured rifles to their North Korean allies for study and potential copying. The rifles arrived at State Munitions Factory No. 65 in Kanggye in early November 1952, carefully packed in wooden crates lined with oiled paper. Kanggye had been chosen as the site for this project because it was located in the mountainous northern interior, relatively safe from American air raids that had devastated facilities closer to the coast and major cities. The factory itself was a modest operation, housed in buildings that had been constructed by the Japanese during their colonial occupation and expanded with Soviet assistance after 1945. It employed approximately 800 workers and had been producing ammunition, basic infantry equipment, and performing refurbishment work on Soviet and Chinese weapons. The factory's director, Choi Sung-men, was a 48-year-old party loyalist who had fought with Kim Il-sung's guerrilla forces against the Japanese in Manchuria during the 1930s. His technical knowledge was limited, but his revolutionary credentials were impeccable, and in the political climate of the early 1950s, credentials often mattered more than competence. When the directive came from Pyongyang to reverse engineer and manufacture copies of the American rifle, Choi understood that this was both an opportunity to demonstrate the superiority of socialist production methods and a dangerous assignment where failure could have severe consequences. He assigned the project to his senior weapons engineer, Pak Min-ho, a 32-year-old university graduate who represented the new generation of technically educated North Koreans. He had studied mechanical engineering at Kim Il-sung University in Pyongyang, though his education had been heavily influenced by Soviet textbooks and teaching methods, with little exposure to Western engineering practices or modern manufacturing techniques. He was intelligent, dedicated, and possessed a genuine aptitude for understanding mechanical systems. He was also about to confront the limits of what education and dedication could achieve without adequate infrastructure and resources.
The deceptive simplicity of genius. When Pak first examined the M1 Garand rifles in the factory's small engineering office, his initial reaction was a mixture of professional admiration and growing concern. The rifle's external appearance was deceptively straightforward: a wooden stock, a metal receiver and barrel assembly, a trigger mechanism, and sights. But as he began to disassemble one of the rifles, carefully removing each component and laying them out on a clean work surface, the true complexity of the design revealed itself. The Garand's operating mechanism was unlike anything produced in Soviet arsenals or taught in Pak's university courses. It used a gas-operated system where propellant gases were tapped from a port near the muzzle and directed rearward to drive an operating rod, which in turn rotated and unlocked the bolt, extracted and ejected the spent cartridge case, and then, powered by a return spring, stripped a fresh cartridge from the en-bloc clip and chambered it while relocking the bolt. The entire cycle occurred in approximately 1/10 of a second and required precise timing and dimensional accuracy to function reliably. The rifle consisted of 67 major components, not counting small springs, pins, and screws. Each component had been carefully designed and manufactured to specific tolerances. The receiver, the main body of the rifle that housed the operating mechanism, was machined from a single forging of ordnance-grade steel. Pak's measurements with the factory's micrometers revealed tolerances held to within 1/1000th of an inch in critical areas. The internal surfaces were smoothly finished, with no visible tool marks or irregularities that might interfere with the smooth reciprocation of the bolt assembly. The barrel was equally impressive from an engineering standpoint. It was manufactured from chrome molybdenum alloy steel, hammer-forged for strength, and then precision-rifled with 6 grooves in a right-hand twist, completing one full rotation every 10 inches. This twist rate had been carefully calculated to stabilize the .30-06 cartridge's 150-grain bullet in flight. The barrel's bore was chrome-plated, a process that provided exceptional resistance to corrosion and erosion from the hot gases and copper fouling produced by firing thousands of rounds. The chamber, the portion that held the cartridge during firing, was precisely reamed to dimensions that ensured reliable feeding, chambering, and extraction while containing the tremendous pressures generated when the cartridge fired. Pak assembled a team of 7 engineers and technicians to work on the project. His deputy was Han Young-sik,
a 26-year-old recent engineering graduate who brought enthusiasm and theoretical knowledge but limited practical experience. The team also included Dr. Ri Kyung-soo, the factory's metallurgist who had been trained in Japan during the colonial period and possessed valuable expertise in steel composition and heat treatment. Master machinist Oh Hyun-roo, a skilled craftsman in his late 50s who understood the capabilities and limitations of their equipment better than anyone, and several younger technicians who would handle detailed measurements, documentation, and component testing. The team's first task was to completely document the captured rifles. They disassembled all 3 examples, compared them component by component, took precise measurements of every dimension, and created detailed drawings that would guide their manufacturing attempts. What emerged from this documentation phase was a sobering realization. The M1 Garand was an extraordinarily sophisticated weapon that had been optimized through years of design iteration and testing. John Garand had begun work on semi-automatic rifle designs in the 1920s, and the rifle that bore his name didn't enter service until 1936, after more than a decade of development and refinement. The seemingly simple gas-operated mechanism had been carefully tuned to function reliably with the wide range of ammunition conditions encountered in military service, from Arctic cold to tropical heat, with ammunition stored in varying conditions and subjected to rough handling. The rifle's designers had access to America's advanced steel industry, which could produce specialized alloys to consistent specifications. They had precision manufacturing equipment capable of holding tight tolerances across production runs of millions of components. They had sophisticated testing facilities where prototypes could be subjected to thousands of rounds of live fire under controlled conditions, with failures analyzed and corrected. They had a deep bench of experienced engineers and machinists who understood the practical realities of mass production. Pak's team had none of these advantages. They had 3 captured rifles, limited documentation, outdated equipment, inconsistent raw materials, and a 6-month deadline imposed by military planners who understood little about the challenges of precision manufacturing.
The Metallurgical Challenge. Dr. Ri Kyung-soo took responsibility for analyzing the materials used in the Garand's construction. This was critical work, as the rifle's performance and reliability depended fundamentally on the properties of the steels used in its manufacture. Using acid etching and microscopic examination of the metal's grain structure, Ri could infer some information about composition and heat treatment, though his analysis was limited by the relatively primitive equipment available at the factory. The receiver appeared to be manufactured from a medium carbon alloy steel, possibly containing nickel and chromium for strength and toughness. The heat treatment had produced a fine-grained structure with excellent mechanical properties, strong enough to contain the forces generated during firing, yet tough enough to resist crack propagation and catastrophic failure. Ri estimated the material had been heated to approximately 1,550 degrees Fahrenheit during heat treatment, then oil-quenched for rapid cooling, and finally tempered at a lower temperature to achieve the optimal balance of hardness and toughness. "We can approximate this steel composition," Ri told Pak during a progress review meeting in late November. "The steel mill at Hamhung can produce a medium carbon steel with chromium and molybdenum additions, but I must warn you, their quality control is inconsistent. The carbon content can vary by several tenths of a % between batches, and the alloying elements are not always uniformly distributed. This will affect the properties we can achieve with heat treatment." The barrel steel presented even greater challenges. Ri's analysis indicated a more specialized alloy, likely a chrome molybdenum steel specifically formulated for gun barrel applications. This steel needed to be exceptionally strong to contain the high pressures generated during firing, approximately 50,000 pounds per square inch when the .30-06 cartridge detonated, while also being tough enough to resist cracking from the rapid heating and cooling cycles that occurred with sustained firing.
The chrome plating inside the bore is also problematic. We don't have electroplating equipment capable of depositing chromium to the required thickness and uniformity. Chromium plating requires specialized rectifiers, carefully controlled plating baths, and specific procedures I have only read about in technical literature. Without it, our barrels will wear more rapidly and will be more susceptible to corrosion. Pak listened to these assessments with growing concern, but he also understood the political reality they faced. They could not simply report to Director Choi and the military representatives that the project was impossible with their current capabilities. Such defeatism would be interpreted as insufficient revolutionary spirit, possibly as sabotage or counter-revolutionary thinking. They had to proceed, document the challenges they encounter, and do their best with available resources. The small components, springs, pins, extractors, ejectors, presented their own manufacturing challenges. Many required specific spring steels with carefully controlled properties. The extractor spring, for example, had to provide sufficient tension to grip the cartridge rim during extraction, but not so much tension that it impaired the bolt's rotation during locking and unlocking. The hammer spring had to be strong enough to ensure reliable primer ignition, but not so strong that the trigger pull became excessively heavy. Each of these components had been optimized through testing and refinement in American arsenals. Pak's team would have to recreate this optimization through their own testing, with limited time and resources.
Manufacturing compromises. By December 1952, Pak had developed a manufacturing plan that he knew represented a series of compromises with the ideal. They would order forged steel blanks for receivers from the Hum steel mill, specifying the best available alloy composition. Master Machinist O would manufacture receivers using the factory's machine tools, a mixture of Japanese-era lathes and milling machines, supplemented by some Soviet equipment. The barrels would be produced by adapting their existing rifle barrel manufacturing equipment, currently used for producing Mosin-Nagant rifle barrels. Small components would be manufactured in-house from available materials. The wooden stocks would be carved from Korean walnut by the factory's small woodworking shop. The steel blanks arrived in late December and immediately revealed quality control problems. The forgings varied in dimensions beyond acceptable limits, requiring additional machining that consumed time and material. More seriously, metallurgical testing of sample pieces revealed significant variation in chemical composition. Carbon content ranged from 0.38% to 0.47% across the batch, when consistency within 0.05% would have been desirable. The chromium and molybdenum additions were similarly inconsistent. This will affect heat treatment results, Dr. Ree warned. Steel with higher carbon content will harden more during quenching, but will also be more brittle. Lower carbon pieces will be tougher, but softer. We'll have receivers with different strength characteristics, which means unpredictable performance and reliability. Director Choi dismissed these concerns when Pak brought them to his attention. The party has determined that Korean steel is adequate for manufacturing weapons. Your responsibility is to work with what our socialist industry provides and make it succeed. Excessive focus on small variations is bourgeois perfectionism. Pak said nothing more to Choi, but he quietly instructed Ree to test each receiver blank and segregate them by carbon content. They would use the blanks with properties closest to the target composition for their initial prototypes, saving the more problematic pieces for later when they better understood the steel's behavior. Master Machinist O began work on the first receiver in early January 1953. O was a craftsman of the old school, trained in Japanese arsenals during the colonial period with an intimate understanding of machine tools and metal cutting. He studied Pak's drawings carefully, examined the American receiver repeatedly, and then set to work with methodical precision. The receiver required dozens of separate machining operations: turning, milling, drilling, reaming, broaching. Each operation had to be performed in the correct sequence with careful attention to holding tolerances and maintaining perpendicularity and parallelism of critical surfaces.
O worked slowly, measuring after each operation, adjusting his techniques to compensate for the limitations of his equipment. The lathe had worn ways that introduced a slight wobble in its spindle. O had learned to compensate for this through careful tool positioning and multiple light cuts rather than attempting to remove material in single heavy cuts. The milling machine was in better condition, but still lacked the rigidity and precision of modern equipment. O used sharp tooling, light cuts, and frequent measurements to achieve the best results possible. After 3 weeks of intensive work, the first receiver was complete. When Pak examined it, he felt conflicting emotions. O had done remarkable work given the limitations of his equipment. The receiver was dimensionally close to specifications, and the critical surfaces were reasonably well finished. But it was also clearly inferior to the American original. The tolerances were looser, with variations of several thousandths of an inch in areas where the American receiver held within 1/1000th of an inch. The surface finish was rougher, showing visible tool marks in some areas, and the weight was nearly 3/4 of a pound heavier than the American receiver, as they had increased wall thickness in several areas to compensate for the uncertain steel properties. The barrel manufacturing was assigned to Factory 447, a specialized facility in Hunan Province with experience in rifle barrel production. They received detailed drawings and a sample section from one of the captured Garand barrels. The factory's engineers studied the specifications, the bore diameter, the rifling dimensions, the twist rate, the chamber specifications, and began production. The barrels that arrived back at Kanggye in February were adequate, but clearly not equivalent to American standards. The rifling was less precise, with groove depths that varied along the barrel's length due to limitations in the button rifling process used by the Chinese factory. The bore finish was acceptable, but not chrome-plated, as that capability simply didn't exist in available facilities. The chamber dimensions were close but not exact, which Pak knew could cause feeding and extraction problems. The gas system components, the gas cylinder, the piston, the operating rod, required close attention to dimensions and fit. The gas port itself, a small hole drilled through the barrel wall near the muzzle, had to be exactly 0.078 inches in diameter. This port size had been carefully determined by American engineers to provide the correct volume of gas to reliably operate the action across a wide range of ammunition types and environmental conditions. Too small, and the rifle would short-stroke, failing to fully cycle the action. Too large, and the system would be overgassed, causing violent operation, accelerated wear, and potential damage to components. The factory's drill bits, worn from extensive use and impossible to replace with American supplies unavailable, tended to produce holes slightly larger than their nominal diameter. The gas port ended up at 0.93 inches, nearly 20% larger than specification. Pak knew this would cause problems, but without proper-sized drill bits or the ability to manufacture them, he had no better alternative.
The first test and its lessons. By late February 1953, the first prototype was complete. Designated the Type 53 rifle internally, the designation had been changed from Type 52 as the project had slipped past its original schedule. It superficially resembled the M1 Garand, but betrayed its compromises to any experienced eye. At nearly 11 pounds loaded, it was substantially heavier than the American original's 10.2 pounds. The finish was cruder, with visible machining marks and a parkerized coating that was unevenly applied. The wooden stock, while well crafted by the woodworking shop, lacked the precise inletting and fit of American production. The test firing was scheduled for March 2, 1953, at the Kanggye Small Arms Proving Range. This facility consisted of little more than earthen berms in a frozen valley, but it was adequate for basic function testing. Pak brought his entire engineering team to observe, along with Director Choi, several military representatives including Colonel Han from the Korean People's Army Ordnance Department, and a political officer whose role was to ensure ideological correctness and report any signs of defeatism.
The rifleman selected for the test was Sergeant Kim Il-sung, an experienced soldier who had fought the Japanese in Manchuria and then the Americans in Korea. Kim had extensive experience with various weapons and could provide informed feedback about the rifle's handling and performance. The morning was brutally cold, with temperatures around -15 degrees Celsius. The ammunition consisted of 50 rounds of captured American .30-06 cartridges, carefully preserved for this moment. If the rifle functioned with American ammunition, they would then test it with Chinese-manufactured cartridges, as they obviously couldn't depend on captured supplies for production weapons. Kim loaded the first 8-round N-block clip, the distinctive curved metal guide that held cartridges in a specific orientation for feeding. The clip slid into the rifle's action from above with a satisfying click. At least the feed system dimensions were correct. Kim assumed a prone position on a canvas mat, aimed at a target positioned 100 meters downrange, and fired. The rifle discharged with a sharp crack, and the empty brass case ejected cleanly, spinning through the cold air and landing in the snow several feet to the right. Kim cycled the trigger again, and a second round fired, then a third, a fourth. The rifle was functioning. Pak felt cautious optimism rising in his chest. Kim continued firing steadily, maintaining good trigger control and sight alignment. The fifth round fired, the sixth, the seventh, the eighth and final round discharged, and the empty N-block clip ejected from the rifle with the characteristic ping sound that every American GI knew. For a moment, Pak thought they had achieved success. The rifle had fired a complete clip without malfunction. But when Kim attempted to load a second clip, the bolt would not lock back. He tried to manually retract the operating rod, but it moved only slightly before jamming solid. Pak hurried forward with Han, and they carefully took the rifle from Kim's hands. It was hot, despite the freezing temperature, the barrel radiating heat from the 8 rounds fired in rapid succession. They carried it to a makeshift workbench, boards laid across empty ammunition crates, and began diagnosis. The problem quickly became apparent. The oversized gas port had allowed excessive gas pressure into the operating system. This overpressure had driven the operating rod and bolt carrier rearward too violently, causing the bolt to impact the rear of the receiver with excessive force. The receiver, made from inconsistent steel that hadn't been properly heat-treated, had deformed slightly at the impact point. The bolt was now wedged in place, unable to move forward or backward. They eventually freed the bolt by carefully tapping it with a brass mallet and punch, but the damage was done. The receiver showed visible deformation, and closer inspection revealed a hairline crack propagating from one of the locking lug recesses, a stress concentration point where the bolt's rotational lugs engage matching recesses in the receiver. Colonel Han's displeasure was evident. The American rifle can fire thousands of rounds without such failures. This rifle failed after only 8 rounds. This is completely unacceptable. Pak tried to explain the technical challenges, the gas port being oversized, the steel quality issues, the manufacturing tolerance difficulties. But Colonel Han was a combat officer, not an engineer. He understood battlefield effectiveness, not the intricacies of metallurgy and precision manufacturing. "You have 4 months to correct these problems," Han said coldly. "The party does not accept excuses. It expects results."
Iterations of failure. The months that followed were a blur of exhausting work, repeated failures, and mounting desperation. Pak and his team built 6 more prototypes between March and June 1953, each incorporating modifications intended to address problems discovered in previous versions. They reduced the gas port diameter, though they still couldn't achieve exactly the correct dimension. They modified the heat treatment process for receivers, attempting to achieve better and more consistent properties. They adjusted spring rates, refined dimensions, and experimented with different surface treatments. Each prototype represented weeks of intensive labor by the team. Each required ordering more steel blanks from Humhung, machining by O and his small team of machinists, assembly of dozens of components, and then testing. And each revealed new problems that hadn't been anticipated.
The second prototype solved the overgassing issue somewhat by reducing the gas port diameter, but introduced a new problem. The extractor would occasionally rip through the cartridge case rim instead of gripping it properly, leaving a stuck case in the chamber that required tools to remove. Investigation revealed that the extractor spring, manufactured from available spring steel, didn't have quite the right characteristics. It was either too weak, allowing the extractor to slip off the rim, or too strong, causing excessive friction during bolt rotation. The third prototype addressed the extractor issue, but revealed problems with the trigger mechanism. The sear engagement, the interface between the trigger and hammer, where the hammer was held cocked until the trigger released it, would occasionally fail to release cleanly, requiring multiple trigger pulls, or resulting in unintended full automatic fire as the hammer bounced and re-engaged improperly. This was traced to improper surface finish and dimensional tolerances on the sear and hammer engagement surfaces. The fourth prototype functioned reasonably well with American ammunition, but had reliability problems with Chinese-manufactured .3006 cartridges. The Chinese ammunition had different dimensional characteristics and pressure curves compared to American production, and these subtle differences were enough to disrupt the carefully balanced timing of the Garand's operating cycle. Sometimes the bolt would short-stroke, failing to fully extract and eject the fired case. Other times it would fail to strip the next cartridge from the clip properly, leaving a feeding jam. With each failure, Pak's understanding of the M1 Garand deepened, but so did his appreciation for how difficult it would be to successfully replicate. The rifle was an integrated system where every component had been optimized through years of testing and refinement. Jean Garand and the engineers at Springfield Armory had conducted thousands of test firings, analyzing failures, making incremental improvements, and gradually converging on a design that worked reliably across the wide range of conditions encountered in military service. Pak's team was trying to compress this evolutionary process into a few months, working with inferior materials and equipment, without access to the accumulated knowledge and experience that had guided the American development effort. It was like trying to recreate a master painting after seeing it only once, using brushes made from weeds and pigments ground from rocks. The political pressure was relentless. Director Choi held weekly progress meetings where Pak had to report on status and timeline. The military representatives visited monthly, growing increasingly impatient with continued delays and problems. The political officer wrote reports documenting insufficient revolutionary fervor and excessive focus on bourgeois technical details. By June, Pak was sleeping only 4 hours a night, spending every waking moment at the factory. His team was similarly exhausted, working 18-hour days 7 days a week. The strain was visible in their faces, in the mistakes that crept into their work from fatigue, in the occasional outbursts of frustration when yet another problem revealed itself. Pak knew, though he couldn't yet admit it openly, that they were not going to succeed. The fundamental problem was not effort or dedication. No one could question his team's commitment. The problem was systemic. North Korea in 1953 simply did not have the industrial infrastructure to manufacture precision weapons to American standards.
The explosion that ended everything. The seventh prototype, completed in late June 1953, represented the culmination of all the lessons learned from previous failures. The gas port was now closer to the correct dimension. The heat treatment of the receiver had been optimized as much as possible with available steel. The extractor spring had been carefully tuned. The trigger mechanism had been refined. Initial testing with limited live firing showed promising results. The rifle had successfully fired approximately 200 rounds of American ammunition over several range sessions with only minor stoppages. The final test was scheduled for June 28, 1953. This would be an endurance test with Chinese-manufactured ammunition, since any production weapon would have to function reliably with domestically produced cartridges. The test protocol called for firing 100 rounds in strings of 8, with brief pauses between strings to allow the barrel to cool slightly, simulating sustained combat firing. The ammunition had been provided by Chinese allies specifically for this test. It looked identical to American .30-06 cartridges, with brass cases, copper-jacketed bullets, and percussion primers. But it had been manufactured to different specifications, using different propellants and loading procedures, in factories with different quality control standards. Sergeant Kim, the same soldier who had tested the first prototype, was again assigned as the test rifleman. Despite his previous experience with the jammed rifle, he had volunteered to continue testing, displaying the kind of courage and dedication that Pak found both admirable and humbling. The morning was less bitterly cold than the March test had been, though still well below freezing. Kim began firing methodically, maintaining a steady rhythm. The first clip of 8 rounds fired and ejected normally. The second clip also functioned correctly. The brass cases glittered in the snow as they ejected, and the rifle's sharp reports echoed off the valley walls. By the fourth clip, 32 rounds total, Pak was beginning to feel genuine hope. Perhaps they had finally solved the major problems. Perhaps this rifle would prove acceptable for limited production. Perhaps all the months of exhausting work would pay off. Kim loaded the 5th clip and resumed firing. The first 2 rounds of the clip discharged normally. The 3rd round fired, and then the rifle exploded. The sound was different from a normal shot, a deeper, more violent detonation accompanied by a visible flash. Kim screamed and fell backward, the rifle flying from his hands in pieces. Pak ran forward, his mind struggling to process what had happened. The rifle had disintegrated. The receiver had shattered into multiple large fragments. The barrel had separated completely. The wooden stock had split along its length. And Kim was on the ground, blood spreading across his winter uniform from multiple wounds. The medics reached Kim first, and Pak forced himself to focus on the destroyed rifle rather than the injured soldier. The medics knew their work, and he needed to understand what had happened. The receiver fragments told a clear story. A long crack ran through the receiver, originating from the locking lug recesses. The bolt had been blown rearward with such tremendous force that it had punched through the rear of the receiver before fragmenting. Metal fragments were scattered across a 20-meter radius. The investigation that followed revealed what had occurred. One cartridge in the Chinese ammunition batch had been loaded with excessive propellant, a quality control failure in the ammunition factory. When this overcharged round fired, it generated chamber pressures far exceeding the .30-06 cartridge's design limits, perhaps 70,000 or 80,000 psi instead of the normal 50,000 psi. A genuine M1 Garand, manufactured from properly specified steel with correct heat treatment, might have survived this overpressure event with damage but without catastrophic failure. The American receivers had safety margins built in, and the steel's toughness would resist crack propagation. But Pak's prototype receiver, made from inconsistent steel, improperly heat-treated, with stress concentrations from imprecise machining and previous damage from the overgassing issue, had failed catastrophically. The receiver cracked, the bolt blew backward with nothing to contain it, and the rifle essentially turned into a fragmentation grenade in Kim's hands. Kim survived, but his injuries were severe. His right arm was torn open by metal fragments, requiring extensive surgery and leaving him with permanent loss of function. His chest was multiple lacerations. His face was peppered with small metal fragments, some of which couldn't be safely removed and would remain embedded for life. He would never fire a rifle again. His military career was over. Pak visited Kim in the hospital 3 days later, carrying a precious bottle of antibiotics he had obtained through unofficial channels. Medical supplies were scarce, and infections were a serious risk. Kim was heavily bandaged, his right arm immobilized in a cast, his face swollen and discolored. "I'm sorry, Comrade Sergeant," Pak said, the words seeming utterly inadequate. Kim looked at him with eyes that seemed much older than his 32 years. "Not your fault, Engineer Pak. You tried to build something we don't know how to build. The fault is with those who demanded the impossible and called it revolutionary spirit." Those words haunted Pak. They still do, decades later.
Reckoning and reassessment. The project was terminated 5 days after the explosion. Pak was summoned to Pyongyang for a meeting with a panel of military officers, party officials, and industrial administrators. He traveled to the capital expecting arrest, possibly execution. The political climate was such that failure could easily be interpreted as sabotage or counter-revolutionary activity. The meeting was held in a cold, austere conference room in a government building. Pak stood before the panel and delivered a detailed technical report on the project, the challenges encountered, the solutions attempted, the reasons for ultimate failure. He spoke for nearly 2 hours, explaining metallurgy, manufacturing tolerances, the integrated nature of the Garand's design, and the industrial infrastructure requirements for producing such weapons. The questions that followed were harsh and accusatory. Why had he not worked harder? Why had he not shown more revolutionary fervor? Why had he allowed bourgeois technical thinking to undermine socialist production methods? Pak answered as honestly as he dared, walking the dangerous line between technical truth and political acceptability. In the end, he was not arrested. He received a formal reprimand that would remain in his file permanently, damaging his career prospects. He was demoted from senior engineer to junior engineer and assigned to less critical work. But he retained his position at the factory and his freedom. Director Choi was less fortunate. He was removed from his position immediately and sent to a rural collective farm for re-education through labor. Pak never saw him again and never learned his ultimate fate. The official explanation was that Choi had shown insufficient understanding of Juche principles and had relied too heavily on worship of foreign technology rather than trusting Korean workers' capabilities. The project's failure was never publicly acknowledged. The prototype rifles were destroyed, all except one, which was stored in a secure facility for future reference. All technical documentation was classified. Everyone involved was instructed never to discuss the project, even among themselves. The families of workers who had been involved were quietly informed that discussing the project could result in severe consequences. North Korea continued to rely primarily on Soviet and Chinese weapons for the remainder of the Korean War and for decades afterward. Soviet SKS carbines and later AK-47 assault rifles became the standard infantry weapons. When North Korea did eventually develop indigenous small arms, they were simple designs, like the Type 58 assault rifle, essentially an AK-47 variant that matched actual Korean manufacturing capabilities rather than attempting to replicate sophisticated foreign designs.
Lessons written in steel and blood. The failed M1 Garand project became a defining experience in Pak Min-ho's career, shaping his approach to engineering for the rest of his working life. He remained at Factory Number 65 until his retirement in 1985, gradually working his way back up to senior positions as the political climate changed and his technical competence proved valuable. The primary lesson Pak learned was about the nature of reverse engineering and technological development. Copying a weapon was not simply a matter of measuring dimensions and manufacturing components to match. The M1 Garand was not just a clever mechanical design. It was the product of America's entire industrial ecosystem. It required specialized steel mills producing alloys to consistent specifications,
chemical companies developing advanced propellants, machine tool manufacturers building equipment capable of holding precise tolerances, and an accumulated body of manufacturing knowledge and expertise built up over decades. You cannot copy industrial capability by photographing a finished product, Pak would later tell younger engineers he mentored. The rifle we tried to build was not just 70 components assembled together. It was the result of an entire industrial system. The steel mills, the machine tool factories, the quality control systems, the trained workforce, the research institutions, the accumulated experience. We saw the rifle and thought we could copy it. We should have looked deeper and seen the entire American industrial base that made it possible. The project also revealed fundamental truths about the limitations of political ideology in overcoming technical reality. No amount of revolutionary fervor could make imprecise machine tools hold tight tolerances. No amount of ideological correctness could make inconsistent steel perform like precision alloy steel. The laws of physics and metallurgy did not respect party declarations about the superiority of socialist production methods. This lesson was dangerous to speak openly in the political climate of the 1950s and 1960s, but it shaped Pak's approach to every subsequent project. He learned to be conservative in his promises, to honestly assess available capabilities, and to advocate for developing indigenous designs that worked within actual constraints, rather than attempting to copy foreign designs that required capabilities North Korea didn't possess. The human cost of the project, Sergeant Kim's shattered arm and scarred face, was never far from Pak's mind. Every time he reviewed a new weapons project, he thought about Kim lying in the snow, blood spreading across his uniform, his military career ended by a rifle that should never have been tested with ammunition of uncertain quality. That image was a more effective check on engineering hubris than any political criticism session could ever be.
The rifle that outlived its imitators. The M1 Garand continued in American service for decades after North Korea's failed copying attempt. More than 6 million were manufactured by Springfield Armory, Winchester, Harrington and Richardson, and International Harvester. The rifle armed American forces through World War II, Korea, and into the early years of Vietnam. It was widely exported to Allied nations and saw service in conflicts around the globe. General George Patton famously called the Garand the greatest battle implement ever devised. Whether or not this assessment was entirely accurate, the rifle was undeniably effective, reliable, accurate, powerful, and capable of providing American infantry with overwhelming firepower advantages in medium-range engagements. Its semi-automatic operation gave soldiers a critical edge over opponents armed with bolt-action rifles, and its rugged construction ensured it functioned in the brutal conditions of combat across varied climates and terrain. The rifle's design influenced subsequent generations of infantry weapons. The selective fire M14 rifle, adopted in the late 1950s, was essentially an improved Garand with a detachable box magazine and full automatic capability. Even the M1 carbine, though mechanically different, borrowed conceptual elements from Garand's work. The principles of gas-operated self-loading rifle design that Garand pioneered became standard in military weapons worldwide. Meanwhile, North Korea's weapons industry evolved along a different path. Rather than attempting to copy sophisticated Western designs, it focused on producing variants of Soviet weapons, first the SKS carbine, then the AK-47 assault rifle. These weapons were simpler, more forgiving of manufacturing imprecision, and better matched to North Korean industrial capabilities.
The Type 58 assault rifle, introduced in the late 1950s, was essentially an AK-47 copy that could be manufactured with available equipment and materials. This represented a practical acknowledgement of the lessons learned from the Garand failure, even if those lessons were never officially discussed. By focusing on weapons they could actually build reliably, North Korean arsenals contributed meaningfully to national defense, rather than producing impressive-looking prototypes that exploded during testing.
Reflections across decades. The story of North Korea's failed attempt to copy the M1 Garand is ultimately about the gap between ambition and capability, between desire and achievement. It's about engineers confronting challenges that their industrial system was not equipped to handle, about political pressure distorting technical judgment, and about hard lessons learned through failure and blood. The engineers who worked on the project were not incompetent. Pak Min-ho and his team were intelligent, dedicated professionals who worked to exhaustion, attempting to achieve their assigned goal. Their failure was not personal, but systemic. They were asked to accomplish something that required industrial capabilities North Korea simply did not possess in the early 1950s. The project's failure revealed uncomfortable truths about technological development that transcend political systems and national boundaries. Advanced technology cannot be acquired simply by copying finished products. It requires accumulated knowledge, specialized infrastructure, trained personnel, quality materials, and time, years or decades of sustained investment and development. The M1 Garand itself stands as a monument to what can be achieved when talented engineers have access to adequate resources and infrastructure. John Garand spent more than a decade refining his design, supported by the resources of Springfield Armory and backed by America's industrial might. The result was a weapon that served effectively for more than 30 years and influenced military firearms design permanently. The destroyed North Korean prototype, if it still exists in some forgotten warehouse, stands as an equally important monument, a reminder of the limits of technological shortcuts and the price of attempting to leapfrog developmental stages. Sergeant Kim's scars tell the same story in flesh rather than steel. Both monuments offer the same lesson. Some achievements cannot be stolen or copied, only earned through patient, systematic development of the capabilities required to support them. It is a lesson that applies not just to weapons manufacture, but to any complex technological endeavor. Understanding it requires humility, the willingness to honestly assess current capabilities and to accept that reaching advanced goals requires walking the entire path, not attempting to jump directly to the destination. For North Korea, this lesson came at a cost measured in wasted resources, damaged careers, and Sergeant Kim's permanent injuries. But it was a lesson that ultimately shaped the country's approach to weapons development in more realistic and productive directions. That may be the project's most lasting legacy, teaching through failure what success might never have taught.